In the first one, we have plotted the charge of three different capacitors as a function of voltage. And as we know, the charge is C times V. So when we have plotted in XY direction, the C is the slope of these curves. And we see that the curve A, here the slope is the highest, largest, so this must have the greatest capacitance. And we can also see that if we want to have a certain voltage over the capacitor A requires the most charge, which is consistent with this expression. In exercise B, we have two circular plates that are separated by an air gap. And we are supposed to calculate what is the magnitude of the charge on each plate when connected to a 12-volt battery. So we have two circular plates. So this is in fact a parallel plate capacitor, where these plates are separated by a distance d, and they both have the radius r. So we want to know the Q. So Q is always the product of capacitance and the voltage applied over them. So in this case, the voltage is 12 volts. And this is a parallel plate capacitor. So, and we know from the previous slide that in such a case, the capacitance is the permittivity of free space times A, where A is the area of the one of the plates divided by the distance between them. So there's an air gap. So no dielectric. If we had a dielectric, then we would have to multiply this by some value K, but that is not the case. Well, in fact, the K for air is 1. So anyway, and then we have the voltage. So if we plug in the numbers, the permittivity of free space 8.85 times 10 to the minus 12. One of its units is coulombs per voltmeter times the area. Okay, so the area is of course the area of a circle times pi times the radius 5 centimeters, 0.05 meters squared, divided by the air gap 0.1 times 10 to the minus 3 meters, 0.1 millimeters, and then the voltage 12 volts. So looking at sanity check for units, the voltages cancel, and we have meter here and meter there, so there is a both in denominator, so these guys cancel the meters from here, and we are left with coulombs, which is the unit of charge, so we're good. And in fact the value is 8 times 10 to the minus 9 coulombs, or 8 nanocoulombs. In exercise C, we are supposed to evaluate the capacitance per unit length of a cylindrical capacitor. So we saw the cylindrical capacitor already, so it looks something like this. So there's a conductor here with radius, that's going to be RB, and the outer radius, or the larger radius, is RA. And we knew that the capacitance in this case would be 2 pi E epsilon 0 times the length of the capacitor. By length they mean that this is in fact, it would have some dimension, so pretty much they are referring to a coaxial cable here. So anyway, and divided by ln RA over RB. And capacitance per unit length means that we want to evaluate the quantity C over L, which by moving L on this side, we are left with 2 pi epsilon 0 divided by the natural log. So we get 2 pi times 8.85 times 10 to the minus 12 farads per meter. This is one of the units for epsilon 0 divided by 2.5 millimeters in the argument, and the RB was 0.4 millimeters. And if you plug in the numbers and in the calculator, we get 3 times 10 to the minus 11 farads per meter. So farads are in fact the units of capacitance, and this is same as 30 picofarads per meter, which is option A. As you can see, if we would increase the length of our coaxial cable, the capacitance keeps increasing. And when you make the cable long enough, the capacitance comes so large that it starts to limit the signal data rate. So if you want to transmit data over long distances, you will have to cut down the data rate. And that is another reason why these copper cables are not the best solution for long-range data transmission. In the last exercise, we have 2 identical capacitors to play with, and we are supposed to find the minimum and maximum capacitances that can be obtained by connecting these in series or parallel. So let's first consider the parallel arrangement, so which means they are connected in such a way, and if you will, we can always put the battery in here to have a complete electric circuit. So as we learned, in this case the equivalent capacitor would be simply C1 plus C2, which is 10 microfarads plus 10 microfarads. We get 20 microfarads. And the other case is when we are connecting these two in series. So here's C1, here's C2. Let's have the battery. And the equivalent capacitance or capacitor would have capacitance. Now let's use the little trick that I showed you. So it's going to be the product of the two divided by the sum of the two. So we get 10 microfarads squared divided by 10 microfarads times 2. So these guys cancel, so we have 10 microfarads divided by 2, which is 5 microfarads. And in this case, the correct answer would be option E.
Fate up against a will through the